So the first talk we will have, Katharina is going to tell us about unprecedented automation in using LLMs for planning. So yeah, very excited to hear this talk. Like I said, I won't be a tough timekeeper, but of course we do have to get through the two talks. So
okay.
fire away. Thank you.
Thank you. So yeah, hi, I'm Katharina. I'm a PhD student at Saarland University, and I'm going to present work on automating the generation of prompts for LLM-based action choice and PDDL planning, which is joint work with Daniel Fišer, Jörg Hoffmann, and Alexander Koller. So as we all know, large language models have achieved impressive performance on a lot of tasks, not only from the NLP community, but also from different research areas. And a very active area of research investigates the question to what extent LLMs can do reasoning and planning. And there has already been a lot of work also since we did this project kind of in the last year. A lot has happened, and there are things that we already know, but there are also kind of still a lot of open questions about when, in which cases do LLMs kind of work well for planning tasks and which not, what makes the domain complex and what not. And so what is kind of useful for this is kind of having benchmarks for those LLMs. And one very popular benchmark that has been used is the Plan Bench framework by Mekam et al. And this is what we built upon and where we got our inspiration from. So they have a benchmark for systematically investigating and evaluating reasoning and planning capabilities of LLMs by letting an LLM provide or generate a plan in natural language, giving a natural language description of a domain and a task. And then they translate this natural language plan back into PDDL and have a validator validating this. And this is very useful, but there are a lot of domain-dependent components in this pipeline. So if you want to use it on an IPC domain, different from Bloxword logistics or Depot or the mystery Bloxword, or on a domain that you come up with yourself, you need to provide yourself the natural language descriptions, translations, and also translators for the back translation. And this is where our work comes in. So we provide an approach for automatically converting PDDL into natural language prompts. And in our work, we then use them for LLM-based action choice, so both for plan generation and for using the LLM as a policy. And we compare this also to a more very simple template-based conversion method and to using PDDL as input. And we find that our automated prompts yield similar performance as manually created ones, and overall kind of better performance than using a simple template-based natural language conversion. And this method allows us to run broad experiments on 58 data sets spanning 38 different domains. And we compare different LLM-based approaches and also compared to symbolic planners. Okay, this is the overview of our experimental pipeline approach. And I will start with the PDDL to natural language conversion step. So this is a domain-independent conversion using an LLM and few-shot prompting. And the way in which you're doing this is we prompt an LLM, for example, for the predicates of the domain with some task description about what the LLM is supposed to do. And then we provide 7 manually created examples of a PDDL predicate and the paired natural language snippet. And then at the end, we include the predicate that we actually want the LLM to translate. And here, for example, from the logistics domain, the in-city predicate gets translated into object is in-city, city. And all of the manually created few-shot examples are domain independent in the sense that we use them for all domains that get converted. And you only kind of put in the predicates from your target domain. So if we want to translate a predicate from rovers, nothing changes except for the target predicate here. We do more or less the same for actions. We also have 4 manually created few-shot examples. For the actions, we include the parameters, the preconditions, and effects based on the converted predicates, so with natural language conversions there. And then do the same for the actions. And here's an example of how this looks for Bloxword. So for each predicate and each action, we get a natural language snippet. And then we can use those natural language snippets to actually compose, based on rules and templates, the overall domain and task descriptions. I'm not going to show the rules as in the interest of time, but I'm going to show how an output looks like. So for example, here for Bloxword, our domain descriptions list all possible actions. And for each action, they kind of also list the preconditions. So I can only pick up an object A from the table if it is the case, and so on. Similarly for all effects of the actions. And then we also convert the tasks, which means that we get a natural language description of the initial state and of the goal state. Okay, and then we can have a natural language description of our previously PDDL planning task. I mean, one question that comes up here is, what about the correctness of this? Because we all know that LLMs don't give guarantees, so there's no guarantee that this is actually correct, but this means correct in the sense of how the designer of the domain actually meant it or how we would translate it. It's still, even if it's semantically weird, our approach that combines those natural language snippets makes sure that it's structurally correct and follows the PDDL structure. And I have an example of this here. So let's focus on the on predicate here, which correctly would be X is on Y. If the LLM makes the strange mistake that it says Y is on X, then also in the natural language description, we would get exactly this switch. So now it would say that you can only unstack an object A from B if it's the case that B is on A, which is semantically weird, but this kind of switch happens at all places in the domain. So still everything that is written in this natural language domain, still if you would map it back into PDDL, your logic would still be exactly the same. Your domain would work exactly in the same way. And this is kind of a mistake that the LLM usually is not doing. This kind of very simple, but there are more tricky PDDL domains. So yeah, it's always consistent. And then if we have those natural language descriptions, we can just plug them into any kind of prompt that we want to use for testing then the planning capabilities of LLMs. And in our case, we have 4 setups, 2 plan generation setups, a basic one, like for example, the one that Vamika et al. Used. And then we also test chain of thought. And we use the LLM as a policy in an ACT and REACT setup, which are popular LLM prompting frameworks or mechanisms. Okay, here's an illustration of how the basic setup works. So we have the prompt, which includes our converted natural language descriptions, and we ask the LLM for a natural language plan. This is generated here by the P LLM for planning LLM. And then we have another LLM for translating this back into PDDL. And we can do this using few-shot examples based on those snippets that we got in the previous step. So if we can go from PDDL to natural language, we can go back here also from natural language to PDDL and get the plans and then evaluate them using a validator val. The chain of thought setup works the same way. We just ask the LLM to think step by step because that has been shown to help LLMs in reasoning tasks. So the LLM generates a thought before kind of outputting the actual instruction or the action here. So when we use the LLM as a policy, the overall setup is very similar, but the PLLM only generates a single action at a time that gets translated. And then after validating the action, we have a feedback generator that kind of gives back feedback for predicting the next action. And this is how it looks in the ACT setup. So the LLM only generates a single action. Then we check, okay, this one here is executable, but does not reach the goal yet. So we give the feedback that this action was executed. And then the LLM makes the next prediction, and if this is incorrect and not applicable because the preconditions are not satisfied, the LLM gets this feedback that which concrete preconditions are not satisfied here. So why the action cannot be executed. Yeah. And then it can correct its prediction. And React works the same way, just that we also have thoughts, like in the chain of thought setup. So yeah, for our experiments, we used GPT-4o and via the API last year in December. We always use few shots, but kind of all of them are automatically generated by our approach, except for the ones for the conversion, but for those you never need new ones here. And yeah, we run it on 17 custom data sets and then on 41 IPC data sets, where we restrict the tasks that we actually include in the experiments based on cost or expected cost here. And we only consider PDDL with conjunctive conditions with negations, and also typing is considered. And then in the tables that I'm going to show you, we evaluated coverage, and it's all based on an average of 5 different seeds. Okay, so the first question the first thing we wanted to make sure is that that our automatic conversion, then the prompts that we get there and descriptions do not lead to a worse performance when using the LLM than the ones that were manually created by Mikam et al. And we found that we get very similar performance on all LLM-based action choice mechanisms here. There's some variation, but neither in the one or the other direction, so overall it's quite similar. Okay. If we then look at those different action choice mechanisms, not surprisingly, the basic setup doesn't work well. This has been shown several times from different people, and yeah, LLMs really struggle at this and cannot plan there. Adding thoughts improves the performance as expected, and if we use the LLM as a policy, then we get the highest results here, especially if we use the React framework, which also adds those thoughts. And we restrict the steps to twice the length of a plan generated with a greedy best first search planner with the FF heuristic, because we don't know that the LLM will at some point actually find a plan, so we need some limit here. Okay, we also compare to a random baseline, and as we see, even in the basic setup, the LLM performs much better as a random baseline. So yeah, there's some knowledge that the LLM can make use of for solving those tasks. But if we look at breadth first search, optimal A star with LLM cut, or the satisficing greedy best planner, then we see that the LLM lag far behind here. Although for some of the domains, we see some promising results when we use the React. So there the LLM solves kind of either all of the tasks that we had or almost all of them. We also, as I said, looked at different input versions. So we checked, okay, if we don't use an LLM for going from PDDL to natural language, but just very simple rules, how do the results look then in that case? And we found that overall it's worse than when we use this LLM conversion and then kind of the templates as in the second step. And also overall, with respect to PDDL, the results are a bit mixed. So for basic, PDDL worked better, for ACT worse. But overall, we had the best results with React here. We didn't test React with PDDL and templates because the thoughts for the few shot examples were all kind of natural language based, and it was not clear or not straightforward how to get those, but this could be something to test also in future work. Okay. So if I go back now to the results on the PDDL to NL conversion, I showed that React worked pretty well on some domains, but we had very small tasks, because if you look at what breadth first search was able to do here and at the average length of the plans, we see that they were very simple. So what we then said, okay, for those domains where React worked pretty well, we selected 4 of them and scaled them up. So we generated an additional data set, and as you can see, it's indeed more complex for breadth first search and the optimal planner, and the plans are much longer. And yeah, for the LLM-based action choice mechanisms, performance goes down, but React is the least affected one here. So if we focus on the React results here, we see that it has higher coverage than the state-of-the-art optimal planner on Quipper and Ferry, and similar on Visit All here, and it outperforms the breadth first search on all domains, but yeah, it cannot compete with the greedy best first search planner. And this just kind of, yeah, as I said, we also run it on IPC domains. But here, even React and chain of thought solved less than 25% of tasks on most of the domains. There were only 10 where they solved more than 25%. Those are the ones that are actually separately listed here. And actually, it looks like on some domains, if React works, it works pretty well. And if it doesn't work at all. So there seems to be something that makes some domains more complex than others. And I think there's still a lot of room for further investigations what those differences are or why sometimes it works and sometimes it doesn't work at all here. Okay, so to summarize, we provided a method for automatically converting PDDL benchmarks into natural language descriptions so that they can be used then for different experiments and different contexts for investigating capabilities and limitations of LLMs. And this makes it easy to run experiments on a large set of different domains. And we did this with LLM action choice mechanisms and provide results on a large number of currently existing domains. And we see some promising results with using the LLM as a policy, but there's still a lot of room for improvement compared also to what we have in symbolic planning, of course. So thanks a lot, and I'm happy to take your questions.
So are there any questions in the room? Yes, Nia?
Thank you for your talk. I have two questions.
Yes.
One is about the failures. Is it because it tries to, so specifically about React, is it because it goes into loops so it gets lost while searching, or is it because it's giving you many actions that are not applicable and you run out of the number of steps that is allowed? So if you can comment a little bit on this.
We didn't look into all of the data that we had, but for example, for floor tile and gold miner, we found that often it ends up in dead-end states, for example, where it cannot recover from. So this seems to be in particular difficult for the LLM. So I think most of the cases there, the LLM ended up in dead-end states. And for whether it's more, I think the cases where it reaches the limit, it never reaches it because it only suggests applicable actions, but it's always that there are cases where it suggests actions that are not applicable. But we didn't do a rough evaluation of all of those failure modes.
Okay, thank you.
Thanks for the question. Any more questions? We still have time. Yep.
Thank you for your talk. In the case of classical planning, we normally calculate that change of the value of the fluents, right? And the next state, what will be true or false, we calculate like that. But if you use natural language, probably using LLM, you guess next action, calculate the next action, and you ask LLM again in the next action. And in that case, I can guess for LLM, it might be difficult to calculate sort of the future situation, not the current situation. So, but I guess it might be possible to guess the next situation by LLM. So, are you calculating that kind of state change, or if not, do you think it's a good idea to calculate that kind of situation changes?
So if I did understand your question correctly, that it's whether kind of the LLM is doing those state changes, kind of whether we give the information to the LLM about those. We're not telling the LLM how the state changed. We kind of, in this setup, the LLM needs to keep track in some way itself on this. And I think investigating what happens if you give this information to the LLM explicitly, that this is something that could be very interesting. The reason why we didn't include this for those experiments was also because we were not sure about the increase in the number of tokens that we get if we do this for each of the states intermediately. So I think the new LLMs have much longer context windows, so it could be something to try there. But or maybe there's some way to compress it in a good way, or figure out how to give it to the LLM weight such that you don't have too many tokens where it could get lost. Yeah, thanks for your question.
Yep. So we've got time.
I have a somewhat related question. So when you ran into error cases, you said it ran into dead ends. How much history of these failures did the LLM actually have? So did it only see like the most recent error in an explanation, or did it see like longer horizons that it had already tried so they could reason about it?
We didn't shorten the history, so every action that the LLM predicted and each feedback that it got was part of the history for predicting the next one. We didn't kind of make any abbreviations there, such that everything was still part of the history. Yeah.
Excellent. Well, thank you. Are there any more burning questions? Because we're not super pressed for time. And if not, okay. So thank Katharina. A brilliant talk. Thank you.